Pleasure seekers unite at 11:20 tonight in high altitude. Now in a brand new series for BBC Two Scotland, Richard Hammond discovers that when building engineering masterpieces, it's important not to wing it.
The Airbus A380 is a super jumbo, the world's biggest passenger airliner, almost half as heavy again as a Boeing 747. But building the biggest created unprecedented challenges for its European designers. They needed a radical new approach to wing design, either that or rebuild most of the world's airports. A pioneering marvel of the skies, it's packed with cutting-edge technology. Yet it owes its very existence to the most unlikely breakthroughs and inventions.
Airbus 007 clear, takeoff 32 left, 290 degrees, 8 knots.
This is the Airbus A380, also known as the Super Jumbo Jet. I'm setting out on a journey to uncover the A380's hidden links to brilliant ideas from across the world and throughout history. I'm about to reveal the engineering connections behind the biggest airliner the world has ever seen. You can't help but just be stunned by the sheer size of the thing. It is the only aircraft where the passenger seats run the full length of the fuselage from front to back on both the lower and upper decks. The cabins are 6.5 meters wide. It's the width of it. And 50 meters long. It is huge. The A380 can carry up to 853 passengers, 35% more than its nearest competitor. It's big. It's very big. The wings are immense. 70 family cars could park on each one. But if the wings are too long, it can cause problems. It stands to reason that the world's biggest airliner is going to need the world's biggest wings. And they are absolutely huge. The total wingspan is almost the length of a football pitch. They have to provide enough lift to get 560 tons of people and machinery off the ground. But believe it or not, if these wings were built to a conventional design, they'd need to be even longer, and the A380 wouldn't fit into most of the world's airports. There's no good being able to fly if you've got nowhere to fly to. There are international restrictions on the maximum size of aircraft to avoid collisions as they taxi around airports. The absolute limit on wingspan is 80 meters. The A380's wings must be short enough to fit regulations, yet they must still create enough lift to get the world's biggest airliner into the air. The Airbus designers found a brilliant solution by drawing inspiration from the animal kingdom. But how did they do it? I'm about to take the first steps in my investigation. Aerospace engineer Dr. Peter Barrington thinks I should get a feel for how a conventional wing creates lift. And the best place to do that is in his wind tunnel at the University of Kingston in London. Peter's given me a handheld smoke generator so I can make the airflow visible.
So, Peter, how does it work and how can this help explain it?
Okay, well, basically the key thing to a wing is the cross-sectional shape. And that bends the air around the wing. The wing is able to make the flow go a lot faster on the top than it goes on the bottom.
The shape of the wing is designed so that air moves faster above than below. As a result, the air above the wing is at lower pressure than normal. So the higher pressure underneath the wing pushes upwards, creating lift for the whole aircraft.
You do get the sense that lift, flight, is just a function of that shape of the wing. That's all it can do.
The same smooth flow of air creates lift all the way along the wing. or almost all the way. Peter's about to show me that conventional wings have a serious downside.
If you move a bit this way, see what happens as you come a bit closer to the end. A bit closer.
Out to the tip of the wing.
Exactly, yeah.
There it goes.
The airflow at the wing tip looks completely different. Instead of a clean, steady flow, there's a spiraling whirlpool of air. It's called a wingtip vortex. High-pressure air from underneath the wing is leaking around the wing tip and pushing down on the top surface.
That last 5% of the wing isn't really doing anything for you. It's not generating much lift.
The vortex means the wing tip doesn't provide any lift. So the wing is longer than is really necessary. And for the super jumbo jet, that's a supersized problem. The Airbus designers had to find a way to clip their wings down to size. And it's a story that reveals the secret of soaring like a bird. For the next stage of my investigation, I'm meeting another leading aerodynamics expert. But I hear he can be a bit difficult. His name is Cossack. And he's a steppe eagle, a species named after the wide-open plains of the Central Asian steppe. I'll be honest, he's a big, impressive-looking thing. Cossack is a scavenger by nature, and his lifestyle gives him a very similar problem to the A380. He's gone. To soar high above the plane in search of food, he needs a thermal, a rising column of warm air around 20 meters wide. But like the A380, his wings can't be too long, otherwise his turning circle will take him outside the thermal. So his wings are perfectly adapted for maximum lift with minimum length. And today he has agreed to take part in an unusual experiment. Oxford University zoologist Graham Taylor is going to show me exactly how Cossack deals with wingtip vortices by filming his wings in flight.
So these are little wireless video cameras.
So you can fit cameras to him?
Right, this is the tricky bit.
What do you do with that?
I'm going to try and put this in his face.
Cossack's handlers help him into the Eagle Cam harness. And now he's ready for his close-up.
Okay.
Wow. With a bit of luck, what we're hoping for is that these cameras are pointing along the wings, aren't they?
That's right.
So we might actually see how they work and what they do. It's fantastic. Right.
It's blowing in the right direction for
There it
flight.
goes. Yes, yes, yes. There you go, there you go. Yes, yeah, there's a beauty. Cossack heads for the wide blue yonder, this time broadcasting on Eagle Cam. There, you can see it. That was right along the wing. Is that what we're looking for?
That's what we're looking for.
Cossack can manipulate the feathers at the tips of his wings. To get maximum lift, he curls them upwards until they're almost vertical. This is the key to getting rid of wingtip vortices for highly efficient flight.
When it's actually soaring around in thermals, what you'll see then is that the wings are taking a heavy load the whole time. And as it does that, those wingtip feathers are curled up the whole way through that it's turning around.
It's disrupting this vortex that rolls around the end of the wing.
That's right.
Cossack's using his tip feathers to create what's called a winglet. This natural adaptation acts as a barrier against the vortex, blocking the path of air as it tries to flow around from underneath his wing. So he doesn't need long wings. His shorter, more efficient wings do the job. The question is, can engineers apply the same trick to this bird's wings? In wind tunnel tests, engineer Peter Barrington showed me how airliner wings suffer from spiraling vortices at the wingtips. Now we plan to solve the problem. This modification, inspired by an eagle's wingtip feathers, is called a winglet.
Okay, have a look at the airflow now.
As expected, the main body of the wing has a smooth airflow.
Maybe now we get to the tip.
But here, at the wingtip, there used to be a spiralling vortex.
What do you see?
No vortex.
Now it's smooth. The vortex trying to curl around the wingtip finds its path blocked by the winglet.
So it's as simple as that. Basically, it's a barrier that stops the air getting round.
Exactly.
And as a result of that, we win back this stretch of wing.
Indeed.
The vortex has been forced away from the wingtip and up to the top of the winglet. So the entire surface of the original wing is now creating lift, effectively doing the same job as a longer wing.
That's what the Eagle was doing.
Indeed. I mean, I think if we had as long as the Eagle did to evolve, we could probably get this a little bit smaller.
Winglets can be made almost vertical to keep the total wingspan to an absolute minimum, just like an eagle's wings.
So it turns out eagles are really good at flying.
They are.
Yeah.
Extremely good.
Richard Whitcomb, pictured here on the right, was the aviation pioneer who recognized the vital significance of the eagle's winglet. Throughout the 1970s, as an aeronautics engineer at NASA's Flight Research Center in Virginia, he revolutionized wing design. His smoke test programs for the US Air Force showed that conventional wings suffered from wingtip vortices. But in these full-scale flight tests, with the giant Boeing KC-135 transporter plane, Whitcomb revealed his brilliant solution. He proved that the addition of winglets increased efficiency by 7%, with a corresponding fuel saving because the engines didn't have to work so hard. Nearly 30 years later, winglets play a vital role in getting the A380 off the ground.
It's hard to believe that these tiny little modifications to the wings can make that much difference.
But without them, the wingspan would have to be around 3 meters longer to achieve the same lift. Thanks to winglets, the wingspan is reduced to 79.8 meters, squeezing inside the regulation airport limit with just 20 centimeters to spare.
And the technology behind it has its origins in birds. But then, you would expect birds to know a thing or two about flying.
The world's biggest airliner was saved by one of Mother Nature's innovations. But solving one problem creates another. Once the monster is in commercial service, how do you keep its running costs to a minimum? Because in the cutthroat airline business, every kilo counts.